Assalamu alaikum. It's our 11th lecture of Advanced Electromagnetic Field and Waves. In this lecture, we will continue our previous two lecture, lecture number 9 and lecture number 10, in which we find the electric and magnetic field waves, okay, of a region having three mediums like N1, N2 and N3, and a wave is coming with having an electric field and magnetic field in propagating in some direction. Okay, if you forgot to watch first, please watch the previous lecture number 9 and 10. Then you have to move on this lecture so that you will briefly understood about the concept. Okay, basically, in this lecture, we are going to continue our previous lectures, and in this lecture, we are going to solve transmission and reflection coefficient of electromagnetic field waves. Okay, you can also apply to find for the magnetic field, whereas electric field. Because you know that the tangential components of electric fields are equal, so you can say that E1t equals to E2t. So these are basically the electric field and magnetic field equation in region 1, where the boundary between region 1 and region 2, you know that is at z equals to 0, whereas region 1 concerned, here is the boundary is z is smaller than 0. So in region 1, we already find the electric and magnetic fields. Okay, in previous lecture you can watch from there. So these are the final results of electric and magnetic field in region 1, where your electric field in first region is x cap, because the direction of electric field, you know, that is in the x direction. Okay, so that's why x cap equals to E naught I, which is the amplitude of the coming wave of electric field, and E power iota is common K1Z, which is the wave propagation minus omega t. Okay. Similarly, this is for the coming wave, and whereas for the outgoing wave means reflection back once your electric field coincides with some boundary incident. So this is for incident, and this is some of the wave is reflected back after striking the boundary. So this is for that. E naught r, r means reflected, I means incident. E power minus iota. Why? Because the wave propagation direction now changes for the case of reflection back, so it becomes minus iota k1z plus omega t, because you take minus common, so it becomes plus omega t here. Okay, now, similarly, the equations for the magnetic field is y cap, because you know that the direction of magnetic field is in the y direction. You also understood that electric field, magnetic field, and the wave propagation are always perpendicular to each other. So if your electric field is in the x direction and your wave propagation is in always in the z direction, so it's understood that your magnetic field direction is always in the y direction. But for the case of going wave, it is positive y. For the case of reverse back wave, it is minus. We already know how you can find the direction of magnetic field, either positive or negative, by the rule I already told in my previous lectures. You can watch from there. Similarly, for region 2, because region 2 is lies between the dimension where is smaller than 0 and with 0 z is okay greater than 0 and smaller than d. So this is the basically position of region 2. Okay, so the electric field and magnetic field in region 2 is shown by these equations. Again x cap, because your electric field direction in the x direction. Okay, E naught plus, plus means coming electric field into region 2. Okay, and again similar thing, and E naught minus, because there is another boundary. Okay, there is another boundary between region 2, so some of the wave also reflect back. So for the case of reflection back of electric field, it becomes E naught minus. Again the wave propagation changes, direction changes, so you have to introduce minus sign, okay, with here. Similar for the case of magnetic field, wave equation is in the y direction, and here is basically E naught plus, because here is H naught initially, and basically you know that H naught is equals to E naught by Z. Okay, so that's why it becomes equals to this. Okay, you can find easily by these relations. Minus e power iota k to z minus omega t, because this is for coming magnetic field into region 2, and reverse back of some of the magnetic field wave equation after striking another boundary, reverse back, and this is for reverse back, because you already know there are three regions n1, n2, and n3. I not draw my diagram in this lecture because we already drawn two times in previous lecture. You can watch the illustration of that diagram from previous videos. Okay, and similarly for the case of region 3, because beyond region 3 there is no other boundary, means there is only a wave is going into, and there is no reflection back from region 3. Okay, so that's why it only limits your equation up to going wave, and your going wave is basically the transmitted wave of electric field, and transmitted wave of magnetic field is written by this. Here your boundary is at z equals to d. Here the boundary is at z equals to d. So for the case of boundary at z equals to d, you just have to replace your d by z minus d. Move d here, so it becomes z minus d. Okay, so it becomes z minus d equals to 0. So this is what you have to put instead of d, z minus d, because now your uh, distance changes and your condition is now at z equals to d. So these are basically the three electric field and magnetic field equations in region 1, 2, and 3. Okay, now we have to apply the boundary conditions. Initially, we have given with the two boundary conditions, and the first one is at z equals to 0, and the second one is at z equals to d. So let's initialize our boundary conditions with this. You know that the first boundary condition at z equals to 0, it implies in only first two regions, because this boundary is between region 1 and region 2. And your second boundary condition z equals to d, it basically initialize in region 2 and 3, because this boundary condition is mentioned in region 2 and 3. So first of all, let's first apply the boundary condition of z equals to 0 in region 1 and 2. So you have to put z equals to 0. So you know that here is z, here z, z, z. Again here z, 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 z. So after putting z equals to 0, you will own and taking e power iota, e power omega t, e power omega t, e power omega t, e power omega t. Okay, e power omega t taking common from all these equations, you will get the final common, and you can cancel, so you will only get with e power iota k2 0, because that is 0, 0 multiplied by k2 iota becomes 0. This is for all. In all, you can see exponential power iota kz. So once z is equals to 0, so in power of exponential it becomes 0, and you know that the power exponential power 0 is equals to 1. So you will only left with e power iota omega t, taking common e power iota omega t from all those, and e power iota omega t from all these, taking common and cancels, you will only get with, you will only left with e naught I, okay, here, plus e naught r from here, which is equals to e naught plus from here and e naught minus from here. This one and this one, this and this vanishes. Okay, as I told you how this vanishes. E power iota kz vanishes because in exponential power is 0, so it becomes 1, whereas e power iota omega t taking common from all from this equation first, and from this equation cancels, and you will only left with this, because you know that the tangential components of electric field E is basically continuous or equal. So that's why you combine equals both. If these tangential components are not equal, so you will not do this procedure. Okay. You also know that the tangential components of magnetic field H are also continuous and equal. So that's why we are also supposed to equal our H1, which is equals to H2. Okay, so how we can equal? We can equal also by applying the boundary condition z equals to 0. Now you can apply the same boundary condition on this H also. So after applying boundary condition on this, so again iota kz, iota kz, iota kz, iota kz, z is 0. So in every equation it becomes e power 0, and e power 0 is basically 1. So you will only left with e power omega t in all equations. Taking common cancels both common, and you will only left with e naught I by z1. Okay, you can see e naught I z1 minus e naught r z1. Okay, the magnetic field of region 2, e naught plus by z2, and e naught minus by z2, and minus minus as it is. So these are the two equations. Let them as equation A and equation B. Okay, so now let's initialize our second boundary condition, and you know that our second boundary condition is basically at z equals to d. So you can apply your second boundary condition in region 2 and 3. Okay, so let's first apply our second boundary condition in region 2 for electric field, because you know that the tangential component, the tangential components of magnetic field H are also continuous. So you are applying this on this. So z equals to d, you will left with, so it becomes, when your z becomes equals to d, it will only left with e naught plus, here is the second region, e naught plus e power iota k2. Now z becomes d, so it becomes iota k2 d, whereas plus e naught minus e power iota k2 d. Where is e power iota omega t? Taking common from this, taking common from this, taking common from this equation, e power cancels, you will only left with this equation, e naught plus e iota k2d plus e naught minus e minus iota k2d equals to, with the third region, and the third region is this, and the equation is this, it becomes e naught t, and e power iota k3 z minus d, because here your z equals to d, so it becomes d minus d, d minus d 0, e power 0 becomes 1, so you will only left with e naught t, e naught t. So this is how you can apply your boundary condition z equals to d in your electric field equation. Similarly, you can do the same procedure for the case of magnetic field in region 2 and 3. So in 2 and 3, two region is magnetic field. This, after putting z equals to d, only it replaces k2d. So e naught plus by z2, e naught plus by, I take z2 common from both these and multiply z2 onto the other side. So you can see here is the z2. Okay, so e naught plus e power, this becomes 0, so you will only left, so sorry, this is not 0, e power iota k2d. Okay, similarly minus e2 minus, and e power minus iota k2d, okay, equals to, because taking z2 common from this equation, multiply to the other side, and other side is the region 3, and the region 3 is this e naught t by z3, e naught t by z3, and this z2 comes from the denominator of these equations, and e naught t, and the exponential becomes 1, because you know that at z equals to d it becomes e power 0, and e power 0 is 1, so you will only left with e naught t, and these are the variables z2 by z3. So now these, label these equations as c and d. Now these are your final equations. Now what you have to do further, you have to find first of all and the solution for E naught plus. Then you have to find the solution for E naught minus. Then finally you can easily find the transmission and reflection coefficient we will discuss in this lecture. So stay tuned with us. So let's find E naught plus uh, or either E naught minus first. To do so, you have to do some algebraic relations, and first of all, equation C and D divide. You have to divide it by e power iota k to d. Where is equation C and D? This is equation C and this is equation D. Okay, these are equations C and D. What you have to do, you have to divide your equation C and D with e power iota k to d. After dividing, you have to subtract. Okay, you have to subtract. So here are my equations. When I divide these equations by e power iota k to d, you can see here is e power iota k to d. Cancels with this and this, you will only left with e naught plus divided by e naught plus. Sorry, e naught plus, e naught plus, e naught plus, e naught plus. Okay. Again, you have to divide e power iota k to d with these factors also. When e power iota k2 divides, when it comes in nominator, it becomes minus iota k to d. Here is already e power minus iota k to d, so minus 1, it becomes minus 2, so it becomes e power minus 2 iota k to d with e naught minus. Here also same procedure. Similarly, for this case, you have to divide E naught t by e power iota k to d. When e power iota k to d from comes from denominator to nominator, it becomes e power minus iota k to d. Similarly, for this concern, z2 by z3 e naught t, and you have to divide it by e power iota k to d. When it comes into numerator, it becomes e power minus iota k to d, because as I told you, we have to subtract. So we have to change signs of the this. So you can see this cancels, you will only left with this plus plus, so it becomes 2 e naught minus e power minus 2 iota k to d. Okay, which is equals to here take common e to t. Here is e to t also. Okay, here is e to t also. Okay, so take e to t common and e power minus iota k to d taking common, you will only left with 1 minus z square by z3. Okay, so this is because we are going to solve the relation of e naught minus. So what we have to do, we have to only left with e naught minus, and we have to divide 2 and e power minus iota k to d to the other side to only left with e naught I. So after dividing, 2 becomes goes to here and this goes to here, and this is minus 2 iota k to d. When it comes into the nominator, it becomes 2 iota k to d, and 2 iota k to d minus iota k to d, it becomes plus iota k to d. So this is your final relation of e naught minus. So let's suppose this is your equation 1. Similarly, now you are going to solve the relation for E naught plus. Okay, so how you can solve? You can do the same procedure. Okay, to do so, now you have to do equation C and D. Now you have to divide your equations by e power minus iota k to d. Initially, you divided by plus iota k to d e power plus iota k to d. Now you have to divide your equation C and D with minus e power minus iota k to d. Initially you subtract, now you are going to add. So after dividing these equations by e power minus iota k to d, you can see here is minus iota k to d minus iota, it cancels, you will only left with e naught minus and e naught minus. But when you divide e power minus iota k to d from this, when it e power minus iota k to d from denominator comes to numerator, it adds, so it becomes e power plus iota k to d, e power plus iota k to d, it becomes e power plus 2 iota k to d. Okay, plus 2 iota k to d. Similarly, 2 iota k to d here. Similarly, you have to divide e power minus iota k to d with this. So minus iota k to d comes upside, it becomes e naught t e power plus iota k to d. Similarly, Same thing, and when numerator comes, it becomes e power plus iota k to d. After doing, but I say that you have to add. You by going addition, you can see now e naught minus cancels because this is plus, this is minus, this cancels. Initially we cancel e naught plus values because we are going to solve e naught minus. In this we are going to cancel e naught minus because we are going to solve e naught plus. So you will only left with this plus this becomes 2 e naught plus and e power 2 iota k to d. Okay, which is equals to, again this cancels and take e naught t e power iota k to d common, and you will left with 1 plus z naught by z3. 1 plus z naught by z3. So this is complicated equation because you need to only find e naught plus, move this 2 and this e power 2 iota k to d to the other side. Doing this, this 2 is here and e power 2 iota k to d when comes into the numerator becomes minus 2 iota k to d, and 1 minus 2 becomes minus 1. Okay, so it becomes e power minus iota k to d. So this is your final equations of e naught plus and e naught minus. E naught minus equations let as equation 1 and e naught plus let as equation 2. So that's it for finding e naught minus and plus, because our question, our problem is to solve transmission and reflection coefficient. So what we are going to do further to do so, as we know that the transmission coefficient is basically equals to et by e naught t divided by e naught I, whereas your reflection coefficient is equals to e naught r divided by e naught I. So by swatching these equations, we assume that we need the value of e naught I and e naught t and e naught r to find the relations. Okay, so let's find the value of e naught I and e naught r and e naught t respectively, so that it's easy for us to find the reflection and transmission coefficient. So our next work, let's proceed, is basically now add equation a and b. Where are equation a and b? This is your equation a and this is your equation b. Now what you have to do, you have to add. Okay, by adding these equations, you can see this e naught I plus e naught r equals to e naught plus e naught minus. This is equation a, and equation b is this: e naught I takes z1 common in denominator and multiplies to other side becomes z1 by z2. So you can see z1 by z2, you will only left with e naught I minus e naught r equals to z1 by z2 equals to e naught plus minus e naught minus. Similar. Now what I say that you have to add these equation a and b. So by doing addition, you can see e naught r cancels with e naught r. You will only left with e naught I. Okay, e naught I plus e naught I becomes 2 e naught I equals to this. You have to add. So taking common e naught plus from this two, here is 1, here is z1 plus z2, it becomes 1 plus z1 by z2, taking common e naught plus. Again between plus, for e naught minus common, here is 1 and here is minus z1 by z2, so it becomes 1 minus z1 by z2 e naught minus common. So this is simply addition of both equations. You know how you can add. So you can see now we can easily find e naught I by this relation, by just putting the value of e naught plus and e naught I, and we know the value of e naught plus and e naught I. The value of e naught plus is this, as we find here, and the value of e naught I is this, which we find here. Okay, so let's proceed. So what you have to do, you have to move this 2 to the other side because we are going to find e naught I. So moving to other side, it multiplies divides by here also. So here is the 2 which comes from here, and here is the 2 which comes from here. So 1 plus z1 by z2, taking LCM, it becomes z2 plus Z1 divided by Z2, Z2 plus Z1 divided by Z2, and 2 is comes from here. Here is E naught plus, and you know that E naught plus value is this, you have to put here. Z3 plus Z2 divided by 2Z3, Z3 plus Z2 divided by 2Z3, E naught T e power minus iota k to the E naught T e power minus iota T. I just put it the value of E naught. So this is the value of E naught, okay, and this is the value of this taking LCM. Similarly, here you can see this value taking LCM, it becomes Z2 minus Z1 divided by Z2, and this 2 comes from this taking common, okay, dividing other side, and here is E naught minus, you have to multiply with E naught minus, and here is the value of E naught minus. You can confirm from this Z3 minus Z2 divided by 2Z3, okay, E naught T e power iota k to D. Now E naught T is common, and E naught T is common, take E naught T common, and 2 multiplied by 2 4 plus 2 multiplied by 2 4, taking 4 also common, you will left with this. Here denominator is Z2 Z3, here denominator is Z2 Z3, you have to take LCM, so taking LCM Z naught Z3 is okay, and in numerator you just have to add. But the condition is to satisfy our equations is basically to satisfy, we have to put at z equals at d equals to 0 to satisfy our equations, okay. So at d equals to 0, exponential terms becomes equals to 1 because exponential terms has d. So once you put d equals to 0, what it becomes, it becomes e power 0, and e power 0 is 1, okay. So after you just have to then multiply Z2 multiply by both these, and Z1 multiply by both these. You will get with this, and Z2 multiply by both these minus Z1 multiply by both these. You will get with this. Here Z2 square plus minus Z2 square cancel, plus Z1 Z3 minus Z1 Z3 cancel. You will only left with Z1 Z2 Z1 Z2 means 2 Z1 Z2. I write here 2 Z1 Z2. Similarly, Z2 Z3 and Z2 Z3, it becomes 2 Z1 and Z2 Z3 divided by this relation, divided by this, and E naught T divided by 4 as it is. Understood? Okay, now what you have to do, you have to divide this E naught, E square, Z square, Z3, both of this, so it becomes E naught T. After dividing this, taking 2 common, from this equations, 2 divided by 4, it becomes 1 by 2, so E naught T divided by 2. And once you divide your Z2 Z3 by Z2 Z3, it becomes 1, and when you divide by Z1 Z2 Z2, so Z2 cancels with Z2, you will only left with Z1 by Z3, so Z1 by Z3, okay. So 1 plus Z1 by Z3 or Z1 by Z3 plus 1, okay, both same. Now what you have to do finally you just have to take LCM, so it becomes Z3. After taking LCM, here first not take LCM, just move ET to the other side because you are going to solve transmission coefficient, and you know that transmission coefficient is basically equals to ET by E naught. So how we can find ET by E naught, because you know that E naught I is equals to ET by 2 this. So what we are going to do here, we are moving this E naught I in denominator of E naught T and moving 2 to the other side and this also to the other side. So after doing this, you will get your final relation, and ET divided by E naught I becomes equals to this 2Z3 divided by Z1 plus Z3. Understood? So this is your final transmission coefficient. Okay, now our task also is to find the reflection coefficient. To do so, as you know that here we add, now you have to subtract the same equation A and B to find the reflection coefficient. After subtracting these equations, you will get this. Now you can see by subtracting sign changes, E naught I cancels with the E naught I, you will only left with E naught R plus E naught R becomes 2 E naught R, whereas taking E naught plus common, you will get with 1 minus Z1 by Z2, E naught plus common, and again plus, so 1, this minus minus becomes plus, so 1 plus Z1 by Z2 taking E naught minus common. Okay, again there is an extra factor of 2, move this 2 to the other side. Okay, you can see this 2 multiplies here and this 2 goes here in denominator of other side. Here you can see again there is E naught plus and E naught minus in the relation of E naught R. Now what you have to do, the same thing, you have to put the value of E naught plus and E naught minus in this relation. So here taking LCM of this becomes Z2 minus Z1 divided by Z2 and 2 which comes from here, and E naught plus, and this is the value of E naught plus. You can satisfy from here. This is the E naught plus value. Okay, this Z3 plus Z2 divided by 2Z3, Z3 plus Z2 divided by 2Z3, and E naught T e power minus iota k to D. Same. Okay. Now plus taking LCM of this, it becomes Z2 plus Z1 divided by Z2, and this 2 comes from here. This 2. Okay. And E naught minus. This is the value of E naught minus I wrote. Okay. Now again you can see E naught T and E naught T is common. And this 2 multiplied by 2, 2 multiplied by 2, 4, taking 4 common, so E naught R becomes equals to E naught T divided by 4. Same procedure inside, you have to multiply Z2 by both these, then minus Z1 by both these. After doing, again Z2 with this plus Z1 with this, you will left with, okay, this, and Z2 square cancels with the minus Z2 square, and minus Z1 Z3 cancels with the plus Z1 Z3. You will only left with Z2 Z3, and here Z2 Z3 becomes 2Z2 Z3. Okay, minus Z1 Z3 minus Z1 Z3. Okay, what it becomes, minus Z1 Z2. Okay, again minus Z1 Z2, it becomes minus 2 Z1 Z2. In denominator same Z2 Z3. Now you have to divide Z2 Z3 here also, here also, by dividing by this, taking 2 common. First take 2 common from these equations, and 2 divided by 4 becomes 1 by 2, so it becomes E naught T divided by 2. So Z2 Z3 divided by Z2 Z3 becomes 1 and minus, so Z2 cancels with Z2, you will only left with Z1 by Z3, Z1 by Z3. By taking LCM you will get with this. Now this is the answer of E naught R is equals to this, which is E naught T divided by 2 Z3 minus Z1 Z3 divided by Z3. Okay, and the value and the answer of E naught I is this, E naught T divided by 2 Z1 divided by Z3 plus 1. Now you already find the results of E naught I and E naught R, but our task is to find the reflection coefficient. You know that reflection coefficient is basically the ratio of E naught R by E naught I. E naught R you already find here, which is equals to E naught T divided by 2 Z3 minus Z1 divided by Z3. And E naught I, you know that this. Not this, this is the transmission coefficient. I only telling you about the answer of E naught I. The E naught I answer is this. Okay, E naught T divided by 2, and taking LCM it becomes Z1 plus Z3 divided by Z3. Okay, not take this. This is your transmission coefficient result. I am only saying about the result of E naught I because we need E naught I here. So E naught I result is here. This cancels with this, and in denominator Z3 cancels with Z3. You will only left with your reflection coefficient, and that is equals to Z3 minus Z1 divided by Z1 plus Z3. So this is how you can find the reflection and transmission coefficient. Okay, so this is a very detailed lecture. We start this problem from lecture number 8, then we discussed some in lecture number 9, and finally in lecture number 10 we did this. So that's all for this lecture and for this topic also. In coming lecture we are going to discuss some new topics. Okay, so that's all for today. We solve the transmission and reflection coefficient. Okay, so thanks for watching. Stay tuned with us. If you have further query, you can comment in. Okay, so I will definitely reply your questions. Okay, and do answers. So thanks for watching. Stay tuned with us. Allah Hafiz.